Have you ever stopped to think about what the ripples in a pond, the sound from a guitar, and even the light from your screen all have in common? Well, they're all waves. In this explainer, we're going to break down the fundamental physics of wave motion, and you'll see how they're transferring energy and information all around us, every single day.
Right, so what's the connection? A guitar string, a massive earthquake, your own voice? The answer is, of course, waves. And by the end of this session, you'll see exactly how these seemingly totally different things are all governed by the same beautiful physics. It's all about disturbances traveling through a medium.
So let's get a really clear definition. A wave is a disturbance that transfers energy through a medium, but, and this is the key part, without any net movement of the medium itself. Think about dropping a pebble into a still pond. The ripples, right? They move outward, carrying energy across the water. But if you were to put a little cork on the surface, you'd see it just bobs up and down. The cork itself doesn't travel with the wave. This is crucial. Waves transfer energy, not matter. Okay, so how do these disturbances actually travel? Well, mechanical waves basically come in two main flavors, and the difference between them is all about the direction the particles are moving compared to the direction the wave itself is traveling. Okay, over on the left, you see a transverse wave. In this case, the particles are oscillated perpendicular, think up and down, while the wave itself moves forward. The perfect example is flicking a rope. The wave zips along horizontally, but any single point on the rope is just moving vertically. Now, on the right, we have a longitudinal wave. Here, the particles oscillate parallel to the wave's direction, creating these squished up areas of compression and stretched out areas of rarefaction. Sound is the classic example of a longitudinal wave. Now, the type of wave a medium can support really depends on its elastic properties. See, transverse waves create something called a shearing strain. They try to slide layers of the material past each other. Because of this, they can really only travel through media that can resist that kind of stress, like solids. Longitudinal waves, on the other hand, just rely on compression. And since you can compress solids, liquids, and gases, these waves can travel through all three. That's exactly why you can hear sound underwater, or even through a solid wall. All right, to really get a handle on waves, we've got to move beyond just descriptions and get into measurements. And for that, we need a specific vocabulary and, you guessed it, a mathematical framework to describe their motion. Let's start with the basic anatomy of a wave. It's pretty straightforward. The highest point right up here, that's called the crest. And the lowest point down here is the trough. The amplitude is just the maximum displacement from that middle or equilibrium position, and the wavelength, which we represent with the Greek letter lambda, is simply the distance from one crest to the very next one. Okay, so these four terms are basically the essential building blocks for describing any wave. We've just seen amplitude, A, and wavelength, lambda. Next up is the period, T, which is just the time it takes for one complete oscillation to pass by a certain point. And finally, we have frequency, represented by nu and measured in hertz. This is the number of complete oscillations per second. And you know what? It's simply the inverse of the period. They're two sides of the same coin. Now, don't let this equation scare you. To describe a wave mathematically, we use what's called a progressive wave equation. It looks complicated, but it's an incredibly powerful formula. It lets us find the displacement, y, of any particle at any position x and any time t. So A is just the amplitude we talked about. Everything inside the parentheses is what we call the phase of the wave. K is the wave number, which is related to wavelength. Omega is the angular frequency, which is related to the period. Phi is just the initial phase. And that little minus sign, that just tells us the wave is traveling in the positive x direction. That's it. Next up, let's talk about speed. A wave's speed isn't random. It's actually determined by the physical properties of the very medium it's traveling through. So, what actually dictates how fast a wave can go? Fundamentally, wave speed depends on two things: the medium's elastic properties, that's the restoring force, and its inertial properties, like its mass density. For a transverse wave on a stretched string, the speed v is the square root of the tension, T, divided by its linear mass density, which we call mu. For a sound wave in a gas, the speed is the square root of gamma, that's the adiabatic index of the gas, times the pressure P, all divided by the gas's density rho. The most important thing to take away here is that the speed is a property of the medium itself, not of the wave's frequency or amplitude. So far, we've only been looking at single, well-behaved waves. But what happens when two or more waves are in the same space at the same time? Do they collide and bounce off each other like billiard balls? The answer, it turns out, is way more interesting. What happens is governed by the principle of superposition. It sounds fancy, but it's a beautifully simple rule with some really profound consequences. It just says that waves pass right through each other, and at any given moment, the resulting shape is simply the sum of the individual waves. This one simple idea leads to the amazing phenomenon of interference. So, what happens when two waves that are in phase, meaning their crests and troughs line up perfectly, overlap? Well, you get constructive interference. Their individual amplitudes literally add together, creating a brand new wave with a much larger total amplitude. They team up.
But what about the opposite? What if the crest of one wave meets the trough of another? We say they're out of phase. In this case, their displacements are opposite, and they can cancel each other out. This is called destructive interference. And if the amplitudes are exactly equal, the result can be a momentary flatline, zero displacement. Poof!
Okay, so now let's explore some of the incredible effects that come from all this wave interference. And these are not just abstract ideas in a textbook, they are the very basis for all the music you've ever heard. Okay, check this out. When a wave reflects back on itself, like on a guitar string that's fixed at both ends, the original wave and the reflected wave interfere to create something called a standing wave. It actually looks like it's standing still, just oscillating in place with points of zero amplitude, no movement at all, called nodes. Now, if two waves with slightly different frequencies interfere, you get something called beats. This is that periodic rise and fall in loudness that you can hear, and its frequency is just the difference between the two original frequencies. This is exactly what musicians are listening for when they tune their instruments. And you know, this isn't new science. Just look at this incredible example from the Nellaiappar temple in India. These pillars, carved from a single piece of rock way back in the 7th century, were engineered to produce specific musical notes when you tap them. It's a timeless, absolutely breathtaking demonstration of standing waves and the natural frequencies of a vibrating object. Wow, we have covered a lot of ground. So let's do a quick recap of the key mathematical formulas that are really essential for describing and calculating wave motion. Think of this as your cheat sheet. All right, this slide basically summarizes your essential toolkit. First up, we've got the progressive wave equation. Next, that fundamental relationship, speed v equals wavelength lambda times frequency nu. Then we have the specific formula for the speed on a string, which depends on tension T and linear mass density mu. And finally, the speed of sound in a gas, depending on the adiabatic index gamma, pressure P, and density rho. If you can master these, you'll have the mathematical tools to solve most problems on waves. So when you think about it, from the simplest little ripple to the most complex signals traveling across the cosmos, waves are the universe's primary messengers. They carry the energy and the information that literally shape our reality. We've mastered sound and light for communication, but as we look to the future, it makes you wonder, right? What will be the next wave of communication we learn?